Chemistry is the study of matter and its interaction, and the periodic table of the elements discovered so far is arranged in groups or columns, and periods in the rows, based on the properties of the elements. Now group 1 is known as the alkali metals, and not including hydrogen gas. So these metals react with water to produce a strong base, or an alkali. Now group 2 are the alkaline earth metals, and these exist in the Earth's crust and react with water to produce hydroxides, which are alkaline in nature. And groups 3 to 12 are the transition metals, and from 13 to 16 we have the boron to oxygen groups. Now group 17 are the halogens, so these react with metals to produce salts. And group 18 is the noble gases, so these are inert, but some have been discovered to be reactive at certain temperatures and pressures, and they're stable. And the lanthanides and actinides are known as the rare earth elements or inner transition metals. The elements in the periodic table are the fundamental building blocks of matter, and here we have the structure of an atom with the nucleus in the middle, and that contains protons, which are positively charged, and neutrons, which are neutral or carry no charge. And orbiting the nucleus are the electrons, so opposite charges attract, while like charges repel each other, but the nuclear strong force holds the nucleus together. So for an element in the periodic table, we have the atomic number, or the number of protons, the symbol, and the average atomic mass, which is in atomic mass units, and considers all the isotopes that are stable and exist on Earth. So for the lithium atom, there are 2 such isotopes, which have different mass numbers, and the same number of protons. So therefore subtracting the number of protons from the mass number gives you the number of neutrons. So this atom here is a lithium-6 isotope. And suppose we ionize an electron, then the lithium carries a positive charge. We must be able to connect the masses of substances and the actual number of particles undergoing chemical changes in a chemical reaction, because you can't really count the particles directly. And this connection is provided using the unit of mole and Avogadro's number, which is denoted Na for shorthand. So 1 mole is 6.022 by 10 to the 23, and this can refer to anything. So in the context of chemistry, that could mean a number of atoms, ions, molecules, and so on. So in the periodic table, the average atomic mass is provided, and 1 atomic mass unit is the same thing as 1 gram per mole. And this is also referred to as the molar mass. So therefore the number of moles of a substance is equal to the mass on the molar mass. So for example, you have grams in the numerator and grams per mole in the denominator, which ends up giving you mole in the numerator. The unit of moles can be used to connect the other units in chemistry. So for example, if I want to find the mass of a helium atom, well, we just read the molar mass from the periodic table, and then we multiply this by moles per atom to cancel out the mole. And 1 mole is 6.022 by 10 to the 23 atoms in this context using Avogadro's number. And similarly, given the mass of a proton in atomic mass units, you can find the mass of the proton in a similar way, but in this context, we refer to a particle rather than an atom. And similarly, if we're given a mass of a substance that's produced in a chemical reaction, then we can convert this to a number of moles. And in this context, we can find a percent composition of calcium and chlorine in calcium chloride. And you can find the concentration of a solute dissolved in a solvent. So for example, salt dissolving in water, which will be in moles per litre. And a number of moles also appears in the ideal gas equation, which we can use to determine the other quantity. Mass spectrometry can be used to determine the identity of the isotopes of an element and their relative abundance on Earth. And the process involves injecting a sample in the inlet, and then a heater is used to vaporize a sample, and an electron gun is used to ionize a sample, and then here you have an electric field accelerating the ion, and the magnetic field deflects the ion onto a detector. And the ion may be deflected in both directions depending on its charge. So depending on the mass of the ion, it can be deflected in different ways, so it may miss the detector completely. So therefore the electric and magnetic fields are calibrated to make sure that certain types of masses hit that detector. The mass to charge ratio is measured at the detector, and here is a simplified mass spectrum which shows the different isotopes of carbon. And we'll look at interpreting this mass spectrum to determine the average atomic mass of an element using the atomic masses of the isotopes and their relative abundance. Here is a simplified mass spectrum obtained using mass spectrometry, but note that the actual output is more messy, and you're only expected to interpret this simplified spectrum. So to determine the average atomic mass of the element, which is found in a periodic table, we basically take the sum of the atomic masses of the isotopes, which are weighted by their relative abundance on Earth. And you divide this by the sum of the weights. You can typically omit this step because this should sum to 1. So calculating this out, we obtain the following average atomic mass of carbon found in a periodic table, which is in atomic mass units. So you can see we practically got the exact value in the periodic table for this case, but in other cases, you'll find that the result is slightly off because the actual atomic mass is used in the calculation rather than a mass number, which is an integer. And you can obtain these values using the data from the Physical Measurement Laboratory of the National Institute of Standards and Technology. The average atomic mass of an element in the periodic table is given relative to the atomic mass of the carbon-12 isotope. And this is done to make the average atomic mass, which is in atomic mass units, equivalent to the molar mass, which is in grams per mole. So the mass of the carbon-12 isotope can be obtained using mass spectrometry, and then to convert it into a molar mass, we use Avogadro's number. 1 mole is equal to the following number of atoms. And if you do this calculation, it'll give you the molar mass of the carbon-12 isotope. So effectively, multiplying this equation by Avogadro's number in a numerator and denominator, we don't alter the result, and therefore in the numerator, we obtain the molar mass of the element we're looking at, and in the denominator, we have the molar mass of the carbon-12 isotope on 12. So the average atomic mass in the periodic table is equivalent to the molar mass of the element. We found that the actual molar mass of the carbon-12 isotope is 12 grams per mole. Now suppose we ionize a hydrogen sample, so we obtain several isotopes. So this one here is protium, which has no neutrons, so just one proton, and this one's deuterium, which has one neutron. So using mass spectrometry, you can obtain a mass of a proton, and to obtain a mass of a neutron, you subtract the mass of deuterium from the mass of a protium, because neutrons carry no charge, so they won't accelerate in a mass spectrometer. So recall atomic mass units is equivalent to grams per mole. So a carbon-12 isotope has 6 protons and 6 neutrons, which would give you 12.096. So this is different to the actual molar mass, because this here is a mass defect. So when protons and neutrons fuse together to form the nucleus of the carbon-12 isotope, energy is released. And by Einstein's famous mass energy equivalence formula, this energy is released in the form of mass, and that explains the mass defect. The mass spectrum of the chromate ion is shown below, and assume that only the most common oxygen isotope exists in the ion. And part A asks us to calculate the average atomic mass of the chromate ion, which can be done using the sum of the masses of the isotopes, weighted by their relative abundance. Now in part B, we're asked to calculate the number of neutrons in each chromium isotope. So first we find the mass number for each chromium isotope. So for this one here, we subtract the mass of the oxygens. Okay, so we have 4 oxygens in each ion. So effectively the chromium isotope in this ion has a mass number of 50, and given that chromium has an atomic number of 24, so that's 24 protons, then we just subtract the number of protons from the mass number to get the number of neutrons. And if you do the same calculation for the other isotopes, and for part C you can verify the average atomic mass of chromium using the sum of the masses of the chromium isotopes weighted by the relative abundance. And I'll leave it for you as an exercise. Pure substances are composed of individual atoms or molecules, and others can consist of atoms or ions that are held together in fixed proportions. So the first example is water, which has a formula of H2O in the liquid phase. So here we can see for every 2 hydrogen atoms in each molecule, we have 1 oxygen atom. And this does not change no matter how big the substance is. So in this second example we have table salt. So here we can see there's a 1-to-1 ratio between the sodium ions and the chlorine ions. And in this example, we have neon gas, which consists of 1 type of atom, so that's a pure substance. And in this next example, we have ammonia, which is a gas. So for every nitrogen atom in each molecule, we have 3 hydrogen atoms. And again, that doesn't change no matter how big the sample is. As we saw, for a pure substance, such as water, which consists of H2O molecules in a liquid phase, then we had the ratio of hydrogen to oxygen atoms being 2-to-1. Well, the law of definite proportions extends this to the mass of the sample. So in other words, the ratio of the masses of the constituent elements in a pure sample is always the same. So in this case, 2 hydrogens have an average atomic mass of 2 atomic mass units, and 1 oxygen has an average atomic mass of 16 atomic mass units. And this is the same as grams per mole. So the smallest ratio here is 1 to 8, and suppose we're looking at a sample containing 1 mole of H2O. Well, in this case, for every 1 gram of hydrogen, we have 8 grams of oxygen. And this mass ratio holds no matter how big the sample is. The empirical formula is a chemical formula that lists the lowest ratio of atoms of the elements in a compound, where the ratio has whole numbers. So for example, we have the molecular formula for glucose, then the empirical formula that gives us the smallest whole number ratio is CH2O. So basically the ratio here is for every carbon, we have 2 hydrogens and 1 oxygen. Now this is useful if we analyze an unknown compound in a laboratory to find the percentages of the elements that it comprises, and then these percentages can be transformed into the mole ratio of the elements, and then that leads to the empirical formula of the compound. Acetic acid has the following molecular formula. Find the percentage composition of each element. Well, we can read the molar mass of each element from the periodic table. So we have 2 carbons, 4 hydrogens, and 2 oxygens in that molecule, so we'll just multiply by those numbers. And if we're summing those together, we obtain the molar mass of this molecule. And now we can obtain a percentage composition of each element. So for carbon, and you can do similar calculations for hydrogen and oxygen to obtain the following results. And these should sum to 100%. A pure substance is composed of an unknown compound, which contains the following percentages of carbon, hydrogen, and oxygen. And we're asked to determine the empirical formula for the compound. So what we do is assume a convenient mass of the substance, and if we're multiplying by those percentages, we can determine the mass of each element in the substance. And now we need to convert these masses into a number of moles. So we know the molar masses of each element from the periodic table. So therefore the number of moles of carbon is equal to the mass of carbon over the molar mass of carbon. So the grams cancel and mole ends up in the numerator. And we can do the same calculation for hydrogen and oxygen. And therefore if we divide the number of moles by the smallest possible value, well, we get the following whole number ratio of carbon to hydrogen to oxygen. So therefore our empirical formula is CH2O. Acetic acid has the following molecular formula, and a compound has the same ratio of elements as acetic acid, and we're asked to determine the molecular formula for the compound if it has the following molar mass. Well, the empirical formula for acetic acid has the same ratio of elements, but the smallest whole number ratio. And using the periodic table, we can find the molar mass of CH2O as follows. And now we can divide the molar mass of our unknown compound by the molar mass of the compound given by this empirical formula. And therefore we can multiply each element in our empirical formula by 6, which maintains the ratio of elements. So this here is the molecular formula for glucose, which is our unknown compound. As we've seen, pure substances contain molecules or formula units of a single type, whereas mixtures can contain molecules or formula units of more than one type, and their relative proportions can vary. So here's an example of table salt or sodium chloride dissolved in water. So effectively we have the hydrogen molecules surrounding the sodium and chlorine ions. And here we have the oxidation of ammonia. So in this mixture we have ammonia and oxygen gas molecules. And here we have the combustion of propane and butane. So here we have propane molecules, butane molecules, and oxygen molecules. And here butane has 2 formula units, because we can reduce it to 2 molecules of C2H5, where the smallest whole number ratio of carbon to hydrogen is 2 to 5. And similar to what we did with pure substances, we can do an elemental analysis and also determine the purity of the mixture, which we'll do in the following example. Sodium chloride contains 60.7% of chlorine by mass, and assuming that a solid sodium chloride sample is contaminated with potassium chloride powder, Would the percentage of chlorine be higher or lower in the sample? Well, the percentage of chlorine in potassium chloride powder can be obtained using the molar masses in the periodic table. So we have the molar mass of chlorine over the molar mass of potassium chloride, which gives 47.6% of chlorine in potassium chloride. So therefore, given this percentage is lower than a percentage of chlorine in sodium chloride, then we expect that the percentage of chlorine in the entire sample would be lower. And really have a think about this. A potassium powder comprises 41.1% of potassium by mass. Now the potassium is present as potassium chloride as a solid, which has the following molar mass, and how many grams of potassium chloride are in the powder. Well, we can obtain the mass of potassium using the percentage, and then we need to convert this into a number of moles of potassium, which is the mass of the potassium on the molar mass of potassium, which we can obtain from the periodic table. And we can see that 1 mole of potassium chloride has 1 mole of potassium. So therefore the mass of potassium chloride is equal to the number of moles of potassium, and we multiply this by 1 mole of potassium chloride per 1 mole of potassium. So these cancel, and then to get the mass of potassium chloride, we multiply by the molar mass of potassium chloride. So the moles cancel, so that gives 0.564 grams. Here we represent atoms using the Bohr model, which assumes that the nucleus is in the middle, which contains positively charged protons and neutral neutrons, and the electrons orbit the nucleus like the planets orbit the sun. So this is a simplified model that's good for visualizing atoms. Now the force between two charged particles is known as the Coulomb force, or the electric force, and it's proportional to the product of the magnitudes of the two charges, and inversely proportional to the squared distance between them. So in this hydrogen isotope, or protium, we have opposite charges which attract each other and have a distance of r between them. But in quantum mechanics, the electron is likely to be found somewhere on the sphere, so basically we have an electron cloud, as the electron doesn't remain perfectly at a distance r from the nucleus. And like charges repel each other, so for example these two electrons would experience repulsive Coulomb forces. In atoms and ions, the electrons can be visualized as being in shells, or energy levels, which are represented by periods 1 to 7, with 1 being closest to the nucleus and 7 being the farthest. And similarly in this energy diagram, and these shells or energy levels consist of subshells, which are grouped in blocks in the periodic table. So these are known as the subshells, which are contained in each shell. So at energy level 2, we have S and P subshells, and similarly at energy level 3 and energy level 4, we have S, D, and P subshells. And in each subshell, we have orbitals. So at energy level 2, we have 1 S orbital and 3 P orbitals. And similarly at energy level 3 and at energy level 4, we have S and P orbitals. But when the D orbitals are filled with electrons, you get more attraction to the nucleus and they drop to energy level 3, as we'll see when we look at electron configurations. From quantum mechanics, the actual orbitals in an atom, which are where the electron is most likely to be found, looks different to the Bohr model, where the Bohr model only really represents the shells, for example in this boron atom. So the 1s orbital looks something like this, as a sphere, which surrounds the nucleus of an atom, which I'll represent as a dot. So in the case of boron, 2 electrons are likely to be found in this orbital, around the sphere. And the 2s orbital is also spherical, but further from the nucleus. So again, in the case of boron, you have 2 electrons likely to be found in this orbital, and boron also has electrons in the p orbitals. So these p orbitals are 3-dimensional dumbbell shapes and oriented around the nucleus. And here you have for boron 1 electron likely to be found in the horizontal p orbital and 1 likely found in the vertical p orbital. And the shapes of these orbitals have been obtained from quantum mechanics. When writing the electron configuration for an atom or an ion, we follow 3 general rules, and one of them is Aufbau's rule, which states that electrons are placed in shells, subshells and orbitals in order of increasing energy. And this leads to the second principle, which is Pauli's exclusion principle, which means that electrons are either spin up or spin down, and therefore one orbital can contain at most 2 electrons. And the next principle is Hund's rule, which basically states that empty orbitals are filled with electrons first. So at the same energy level, we fill the empty orbitals first, and then fill those orbitals with electrons. So we're just following this triangle, as we can see. And now we fill the d orbitals. So when these orbitals contain electrons, you're going to get pulled towards the nucleus. Then the d orbitals drop to a lower energy level than the 4s. So that's why using this triangle will help us to maintain the correct order of filling the orbitals. And we'll get some practice in applying these rules using examples. Some atoms do not follow Aufbau's rule when we assemble their electron, and one of those is chromium. So what we do first is assemble the electrons from the lower to the higher energy level, and the number of atoms across each block in the periodic table, so for example the S block, tells us you can only assemble a maximum of 2 electrons in the S subshell. And the P subshell is 6 elements wide, and similarly with the D subshell, and the F subshell takes 14. And let's continue to assemble those electrons from the lowest to the highest energy level. So as we can see for chromium, we have 4 electrons in the D subshell. So therefore the D orbitals get pulled towards the nucleus, so the energy levels drop. So for chromium, 1 electron from the 4s orbital jumps to a 3d orbital, which is a more stable configuration. And from this you can write the electron configuration for chromium. Let's write the electron configuration for silicon. So using this triangle, we can assemble the electrons in order of increasing energy level. So that's Aufbau's rule. And Pauli's exclusion principle states that electrons are spin up or spin down, so there's a maximum of 2 electrons in each orbital. And Hund's rule states that the electrons are assembled in the empty orbitals first. And we continue this process until we get to silicon. So the electron configuration is written as follows, with a subshell in the base and a number of electrons in the superscript. Let's write the electron configuration for iron. And as I assemble the electrons, think about Aufbau's rule, Pauli's exclusion principle, and Hund's rule. So now we can write the electron configuration with the subshell in the base and the number of electrons in the superscript. And as we know, the d orbitals get pulled to the nucleus when they're filled with electrons, so they end up having a lower energy level than the 4s orbital. So we basically just swap these around. We can write the electron configuration of the atoms using a shorthand notation or noble gas notation. So for example, for lithium, we have the electron configuration of helium and 1 electron in a 2s subshell. And similarly for boron, so the electrons in the outer shell of the atom are called the valence electrons, and they're shown here using the Bohr model. Now the ionization energy is the energy required to remove an electron from an atom. And this can be estimated qualitatively using the energy analog of Coulomb's law, which states that the electric potential energy is proportional to the product of the charge of the nucleus and the electron, and inversely proportional to the distance of the electron from the nucleus. So as you can imagine, it's going to be a lot easier to ionize a valence electron. So the Coulombic potential energy is always less than 0, so electrons close to the nucleus are going to have a lower potential energy than the electrons farther from the nucleus. The potential energy of an electron is related to the charge of the nucleus and the charge of the electron, and inversely proportional to the distance of the electron from the nucleus. Now suppose we consider this atom of lithium. Well, the nucleus will attract the valence electron, but the core electrons are going to repel it. So therefore the core electrons are shielding the valence electrons from the nucleus. So therefore we define the effective nuclear charge as the number of protons in a nucleus minus the shielding constant. And here we'll simplify this to the number of core electrons. So therefore the effective nuclear charge on the valence electron is the number of protons minus the number of core electrons. Now suppose here we had a hydrogen atom gaining an electron, and here we have a helium atom, and here we have a lithium atom that's been ionized. So we can write the effective nuclear charge as equal to the number of protons in a nucleus, so therefore the energy that needs to be input to ionize an electron from the lithium ion is going to be the highest among the three. Photoelectron spectroscopy is an experimental method to determine the electron configuration of an atom. So first, a light beam is fired from an electromagnetic radiation source onto a sample, and the photons carry energy in the extreme ultraviolet range, which is invisible to the human eye. And if the photon carries the exact amount of energy to eject an electron, then the electron absorbs a photon and gets ejected. So this is known as the photoelectric effect, and the photoelectron flies at some velocity into an energy analyzer for the binding energy to be computed. So the energy from the electromagnetic radiation source is equal to Planck's constant by the frequency, and that's equal to the binding energy plus the kinetic energy of the photoelectron. And this binding energy is the ionization energy. So from the speed of the photoelectron, the kinetic energy is computed, and this can be rearranged into the following expression. So the energy analyzer counts the electrons with different binding energies, and here is an example of a photoelectron spectrum that's obtained to determine the electron configuration of the atom. Given the following photoelectron spectrum, which is obtained using photoelectron spectroscopy, and this spectrum is idealized as a real one is messy and requires an expert to read it. So each peak here represents a subshell. So an electron in this subshell requires around 6 electron volts to eject it, and for this subshell the binding energy is around 76 electron volts. So following the periodic table, we start at energy level 1 and move to the right and down. So the first peak represents the 1s subshell, and the second peak represents the 2s subshell. So this must be the valence shell, because it's a lot easier to eject an electron, as it has a much lower binding energy than the 1s subshell. And the relative heights of the peaks tell us the ratio of electrons between the subshells. So for every 1 electron in a 2s subshell, there's 2 electrons in the 1s subshell. So therefore, using the periodic table, we have 1s2 and 2s1, which is the electron configuration for lithium. Identify the element in the periodic table represented by the following photoelectron spectrum. So we start from the nucleus and work our way to the valence shell. And you can follow the periodic table to do this, going from each energy level in order. And now we can work out the relative number of electrons. So we know that the subshells closer to the nucleus get filled first, and the s subshells take 2 electrons. So we can see that the p subshell has 2, 4, 6 electrons, and the 3s has 2 electrons, and the 3p subshell, relative to the 1s subshell, has 5 electrons, as we can see. So therefore the electron configuration of our element is written as follows, and that's representative of chlorine. Let's identify the element in the periodic table represented by the following photoelectron spectrum. So we can work our way through the periodic table in order of energy levels. So basically the subshells closest to the nucleus to the valence shell. So what we have is the 1s, 2s, 2p, and so on. And note that the d subshell takes 10 electrons, whereas the p subshell takes 6 electrons. And the s subshells are 2 elements wide, so they take 2 electrons. So knowing this, we can write the number of electrons against each of those subshells. And as we can determine, the 4p subshell, in this case, takes 2 electrons, according to the scale of this graph. So we can write the electron configuration of our element as follows. And this is the electron configuration of germanium. The first ionization energy is recorded as follows. Determine the wavelength of light required to ionize one atom in nanometers, and we're given Planck's constant and the speed of light. And assume the kinetic energy of the ejected electron is 1.248 electron volts, which we can convert to joules. So we know that the energy from the electromagnetic radiation source is equal to Planck's constant by the frequency, and that's equal to the ionization energy plus the kinetic energy of the ejected electron. Now the binding energy is given in megajoules per mole, so we need to convert it in units of joules per atom. And the kinetic energy of the ejected electron can be converted from electron volts to joules. And then you can substitute into this expression and divide through by Planck's constant, which gives you the frequency of light, and the wavelength of light can be obtained using the following expression. So speed of light is the wavelength by the frequency. Then convert this to nanometers. Then use the correct number of significant figures and post your answer in the comments. We can observe certain trends in the periodic table, and one of those is the ionization energy. And if we look at energy level 2 and lithium, for example, and moving from left to right, we can see that the number of protons increase between the elements, and so do the number of neutrons. And given these are neutral atoms, you're going to get an increase in the number of electrons. Now given that the number of shielding electrons does not increase, according to our simplified model, where the shielding electrons are the core electrons, then a nucleus is going to exert a larger force on the valence electrons, and therefore those electrons are going to be more difficult to ionize. Now if we move down the periodic table, we're adding extra shells, and while there were protons being added to the nucleus, there's an equal number of electrons that are being added to the atom, and these effectively shield the nucleus and nullify its effective charge. So therefore, given the valence electron is further from the nucleus and shielded, then the ionization energy is going to decrease as we move down the periodic table. We know that electrons orbit the nucleus of an atom in a cloud in different shaped orbitals, but using the Bohr model, we can visualize the atomic radius as the average distance of the valence electron from the nucleus. Now if we look at energy level 2 of the periodic table, for a simplified example, then as we move from left to right of the periodic table, we're effectively adding protons and neutrons to the atom. And for neutral atoms, we're adding an equal number of electrons. So using the effective nuclear charge, when we take the shielding electrons as the core electrons in our simplified model, then we're not adding any more core electrons, and therefore the effective nuclear charge is increasing because of the number of protons is increasing. And consequently, the atomic radius is going to decrease. Now if we move down the periodic table, we're adding an additional shell, and consequently the atomic radius is going to increase, given that the average distance of a valence electron from the nucleus is going to be larger. The periodic trend for ionic radius is similar to that of the atomic radius. So moving from left to right, the ionic radius is going to decrease because protons will be added to the nucleus of the ion, and the valence electrons will be added to the same shell. So think about this. And as we move down the periodic table towards increasing energy levels, we're going to be adding shells to an ion. Now one thing to note is that if we ionize an atom, such as lithium, we get a positively charged ion, and we can see that the ionic radius of this lithium cation is going to be smaller than the atomic radius of the lithium atom, because you either lose a shell where the electrons orbit closer to the nucleus, or you lose an electron which reduces repulsion. Now in contrast, if an ion gets attached to this fluorine atom, then we get a negatively charged fluorine ion. So due to the additional repulsion, the ionic radius of the fluorine anion is going to be greater than the atomic radius of the fluorine atom. The electron affinity is the energy released when an electron is attached to an atom. So basically the atom becomes an anion. So recall that when an electron is attached to an atom, energy is released in the form of a photon. And we define the electron affinity as a negative of the energy released. So a positive value means that the atom has an affinity for an electron. So with helium, it has a full valence shell already, so therefore another shell needs to be added to attach an additional electron. And therefore energy must be added to the atom for this to occur, and therefore helium has no affinity for an electron. And if you follow similar logic for the atoms at energy level 2, you'll see that beryllium does not have an affinity for an electron, because the next electron would be added to the 2p subshell, and that requires an increase in energy. And using similar reasoning, nitrogen and neon also don't have an affinity for an electron. So you'll see a trend in the periodic table as you move from the left to the right of the p block in particular, where there's an increase in electron affinity. Electronegativity is the ability of an atom to attract an electron from another atom to form a chemical bond. So as we go from the lithium atom to fluorine, you get more protons in the nucleus and valence electrons added to the outer shell, so the shielding electrons do not change, and the effective nuclear charge increases. So therefore, as we move from the left to the right of the periodic table, the electronegativity of the atom increases. And as we move down the periodic table, so towards the increasing energy levels, additional shells get added to the atom, and therefore you have more shielding electrons that reduce the effective nuclear charge of the nucleus, and therefore its capability of attracting an electron from another atom. So therefore the electronegativity decreases as we move down the periodic table. The first ionization energy of neon is higher than that of magnesium because the Coulomb force on a valence electron of magnesium is weaker. True or false? Well, as we know, neon is at energy level 2 and magnesium is at energy level 3 in the periodic table. So given that magnesium has an additional shell and the Coulomb force is proportional to the charge of the nucleus by the charge of the electron, and inversely proportional to the squared distance between a valence electron and the nucleus. Then we know that the Coulomb force on a valence electron of magnesium is weaker. So this is true. And consequently, it's more difficult to ionize a valence electron from neon as it is from magnesium. And generally, recall that when we move from the left to the right of the periodic table, the ionization energy increases because the effective nuclear charge increases, and as we move down the periodic table, due to the additional shell, the ionization energy decreases. An atom of chlorine has a larger radius than a chlorine anion because the effective nuclear charge of chlorine is higher. True or false? Well, an atom of chlorine with an additional electron is the chlorine anion. And because of this additional electron, the chlorine anion has additional repulsion and a larger radius than the chlorine atom. So this statement here is false in itself. And as we define the effective nuclear charge as the number of protons minus the shielding electrons, well, the number of protons is the same between a chlorine atom and the chlorine anion, and so are the number of shielding electrons. So draw the Bohr model for both of these and convince yourself that the effective nuclear charge does not change. So the correct answer is false. Let's arrange the following atoms in order of these increasing atomic properties. Now chlorine's at energy level 3, and the rest of the elements are at energy level 2. So according to our periodic table trend, because chlorine has an additional shell, then it's going to have the lowest ionization energy, and that's followed by nitrogen, oxygen, and fluorine, which have an increase in effective nuclear charge as we move to the right of the periodic table. Now fluorine is going to have the smallest atomic radius, because it's going to be the most effective in pulling those valence electrons towards the nucleus, with the larger effective nuclear charge, and followed by these other atoms, where chlorine has an additional shell and therefore a larger atomic radius. Now the electronegativity, which is the ability of the atom to attract an electron from another atom, increases as we move to the right of the periodic table, and decreases as we move down the periodic table. So we have chlorine, nitrogen, oxygen, and fluorine. And this is the general answer by following the trends in the periodic table, although you'll find exceptions to this general trend. Ionic compounds form when elements, and typically metals, transfer electrons to non-metals. So in this case, two lithium atoms transfer electrons to an oxygen atom, so effectively you get a strong electrostatic attraction between the nucleus of the cation and a transferred valence electron. And this is represented by the following ionic compound, which is lithium oxide. So you have two positively charged lithiums to one negatively charged oxygen, and the net charge on the ionic compound is 0. Now the typical charges in ionic compounds are governed by their location in the periodic table and the number of valence electrons. So to form a stable outer shell, you have the elements in the metal groups losing electrons, and also in the boron group, and the halogens and elements in the oxygen and nitrogen groups gain electrons to form a stable outer shell. And the noble gases and elements in the carbon group are generally stable as they are. And the transition metals can lose a different number of electrons. A number of ionic compounds can be formed from a transition metal, such as copper, which can lose a variable number of electrons. So remember that the metals and elements in the boron group lose electrons to form a stable outer shell, and the halogens and other non-metals gain electrons to form a stable outer shell of 8 electrons. So if we look at the first compound, chlorine gains an electron to have a stable outer shell. So in this case we have 2 chlorines, so therefore copper loses 2 electrons. So because we have copper 2 plus, we call this compound copper 2 chloride. And for this compound, we have bromine in the halogen group, and because copper has a 1 plus charge, we call this copper 1 bromide. And have a go at naming this compound as an exercise. Now elements in the same group tend to form analogous compounds, so here we can see the ratio of charge in sodium chloride is the same as the ratio of the charges in potassium chloride. And the ratio of elements is also the same.